Welcome to the fourth tutorial of the online training course MOOC for modePROCON. Note that for this tutorial the installation of the tool is preconditioned. Up to now, the objectives, the theory behind the tool and the installation procedure should be known from the previous tutorials. In this tutorial, an application of modePROCON is presented and is dealing with surface water. The tutorial is structured in 4 parts. First, the study area is presented and briefly described. Then, the results of the sampling campaigns are shown. modePROCON is used to answer the question if the detected PPCPs can also be found in the extraction wells, and if a model is helpful and if it can be set up. In the end, some model results are presented. Let's start with the study area. The investigated study area is located in central Silesia, which is in the south of Poland. The water treatment plant, Kozlowa Gora, is located in the south of the study area, and it extracts water from the Kozlowa reservoir. The reservoir is fed by the Prinitsa river catchment, which accounts for 193 square kilometers. Overall, it is a rural area covered with woodland or agriculture. Additionally, 10% of the area is artificial, and an airport as well as wastewater treatment plants are located within the area. The river water was sampled at 5 locations along the river to analyze the concentration of all the listed PPCPs in modePROCON. The compounds phos, DIT, carbamazepine, acylsulfame, and oxypurinol were detected in the surface water. Now the question arises if these PPCPs can be detected also in the pumping wells. For this, modePROCON can be used. So here we go. Let's open modePROCON. First, you have to select the water source. For this case, please click on Evaluation below the surface water system on the right. Now you can select the PPCPs we are interested in. Please tick phos, DIT, carbamazepine, acylsulfame, and oxypurinol next to the names. Then click on Evaluation. As a result, you can see for all the selected PPCPs the compound-specific generated indices for solubility, sorbability, volatility, and degradability. These values are also displayed in the figure below the table for each selected PPCP. In addition, you find for each PPCP a link for a study dealing with a particular PPCP in the surface water. The modePROCON algorithm gives also the likelihood of a certain PPCP to be found in the water source. In this case, it is very likely to detect acylsulfame. while to detect carbamazepine, DIT, oxypurinol, and FOS is likely. All the selected compounds are little volatile, with exception of acylsulfame that shows moderate volatility and solubility and show little sorption capacity. Another exception is FOS that shows moderate sorption capacity. Although acylsulfame is moderately volatile, it has the highest probability to be detected in surface water. This is related to the high solubility and very low sorption capacity of this compound. On the contrary, all the other PPCPs show lower solubility and higher sorption capacity. Thus, they can be found less likely in surface water. As all selected PPCPs are likely or very likely to be detected in the surface water, it is recommended to set up a model to further investigate the risk of observing a contamination of the water source. For this, please click on Go to Model Requirements. As you can see here, several data is required to model the surface water flow and the transport of PPCP in the surface water. Thanks to previous hydrogeological reports and studies, as well as development of innovative technologies, much information is available for the river flow velocity, surface water temperature, and digital elevation model. Besides this, we suspect that the interaction with the groundwater may be a source of PPCPs in the study area, and the measured concentration in the aquifer are also known. If we tick all the available information and click on Evaluation, the following output can be obtained. The model cannot be built. modePROCON provides the user with a suggestion how to obtain the missing data. In this case, the source of contamination can be yielded by analyzing seepage water collected in a collection bag of a seepage meter, or with a network of monitoring wells. Another alternative is to solve an inverse problem of unknown contaminant source, for instance, particle backtracking. Potential sources of contamination can be treated wastewater discharge into the rivers, leaking sewers, landfills, septic system, livestock breathing, and agriculture. Intensive research in the study area is then recommended. If we assume to have this information, we can tick on Yes and then click on Evaluation. Now that all the necessary input data are available, the output of modePROCON is it is possible to develop a numerical model. The influence of the water treatment plant was analyzed in this project as well, and some PPCPs can be observed in the influent at low concentration. Even though such low concentrations are not a matter of concern, it can be still interesting to identify where they could come from. Several sources might be the reason for the detected PPCPs in the Vinica River and the Kozlova Reservoir. Since the occurrence is related to the usage of the PPCPs, a conceptual model can help to identify potential sources, as it can be seen, for example, here in the case of acylsulfame. The model suggests that there might be an inflow by runoff water from agricultural land, by wastewater discharge, and by unregistered discharge of anthropogenic areas.